So let's go over what a limit is and the applications and the processes of limits itself. Okay. So first we're just going to look at a graph. And we have a piecewise function here where we have multiple things going on at the same time. Okay. So let's look at just individual parts themselves. So when it comes to what a limit represents and how a limit is defined, think of it as a simply, well, as I walk towards the x value, so as x approaches some number, and it can be any arbitrary x value, I want to figure out what is the output, meaning what would the x of x, f of x equal to? And that's pretty much it. And that's what we're looking for is, well, as I approach here, what would the answer be? And you're always looking at the output, meaning the y values here, or the f of x function itself. So let's look at -6, for instance. So as I go to -6, and I'm going to go in both directions. So if I'm coming from the left-hand side, and this is just me walking, so this is just me simply just walking along, and until I stop when I see actually at -6. And when I see, well, what's the output I would see? So I would just go straight across, because the output's always on the y scale, and I would see -1. So when x approaches -6, my answer would be -1. So on this side, it would be -1. And I'm going to do that for every single point I have. So now what if I go the opposite? So this coming from the left, now let's approach it from the right. So now this time I'm walking in the opposite direction. I'm going this way. I walk towards -6, because it's -6 on this side, on the line itself, and then I stop. And I stop because I'm exactly on top of -6. So therefore, what is the y value I would see, or the f of x value? So I go across, and it's going to be 4. So on the right-hand side, it's going to be 4 as my answer. Okay? And now we can keep going. So what if now x approaches, let's say, -3? So I'm going to do the same process. I'm going to go from the left and from the right-hand side. So this time I'm walking this direction. Walk, until I hit here, which is exactly at -3. And I look at my output, which would be -1, -2, -3. So again, on the left-hand side, it's going to be -3. And now I go from the right-hand side. Starting from here, keep going in the same way. And this time, they actually equal the same number. Okay? And I'm going to do that for a couple more situations. Okay? So same thing, I'll go to -1. So I walk, until I stop. Now this is a bit of a tricky part, because notice we have two different values. But here's the process when it comes to a limit, or the x of x value. So a limit, as abbreviated LIM, isn't the same thing as the actual value would plug it into a function. Is as I approach a value, what would I eventually see? So even though I have an open circle here, here, and there, I'm not going to jump. I'm just going to follow until I have, a cliff, until I see exactly -1. So at this value, I just look straight across, and I see 2. So from the left side, I see 2. And I go the same process, going in this direction. Walk. And then from the right-hand side, I also see 2. Okay. So do a couple more times. We have 3 more traces here. So this time is going to be 1. So if I walk, whoop, stop here. That's at 1. So on the left, I would see -1. And on the right-hand side, I will also see -1. Okay. Well, you may think, oh, this is pretty straightforward. It's kind of about. Limits are very simple that way. So let's go to 5. Walk. Eventually stop. I go across, and it's actually 0. So on the left, it's going to be 0. Walk. So from the right-hand side, will also be 0. Now, let's also look at 8 now. 8's a bit of a trick process. So this is the left side, this is the right side of 8. So if I walk on the left side of 8, well, you may think I stop here, but this is actually going forever. These are arrows going into infinity, just like it is going in that direction. Okay? So as I approach this value, I never really get into it because we actually have something called a vertical asymptote at this individual value. And we know by past experiences, you can never cross a vertical asymptote. It just goes on forever. So technically, I'm going down forever. Well, we have a notation for that. That's called infinity. But the problem is I'm going down, and my y values are actually being more negative, right? Negative 3, 4, 5, so forth, and so forth, so forth. So what we say is this limit actually equals negative infinity. Okay? And the same thing applies on the right-hand side. So if I walk going towards 8, I go again down, going bigger and bigger in the negative direction. So again, this will be infinity, but because we're going in the negative direction, it will also be negative infinity. So the question now becomes, how does the notation represent this limit stuff? It's actually very simple. So the notation for a limit looks like this. It's LIM abbreviates the limit. And in the bottom is exactly here. It says, well, when is x going towards a number? Okay? So let's say we're talking about this one here, negative 3. So as x goes towards negative 3, we want to figure out what is the output. And usually they signify f of x or the function itself we're talking about. But since we don't know what the actual function is, it's just abbreviation for it, what would the output be? Now, when it comes to a limit, like here, the left and the right must agree with one another. So the question is, at negative 3, which is right here, does the left and right agree? And exactly they do. The outputs are both negative 3. So this answer would be negative 3, because they both agree. Now let's go to another one. Let's say negative 1. So if we want to take the limit as x approaches negative 1, again, always on the x scale, right? This is what x is, of our function. And we want to see what is the output. Again, we look at this. Here's negative 1. I go up here. On the left, we got 2. On the right, we got 2. Since they both agree, the answer is 2. Even though it's technically 3, when you plug in negative 1, that's not the actual limit. Limit is what is approaching. Well, it's not the actual value itself. So you may be asking, well, what does it mean it's always going to be an answer? And it actually isn't. This is the reason why I say left and right have to coincide. Let's look at 6. So let's take the limit as x approaches negative 6. So on the left-hand side, we get negative 1. On the right-hand side, we get 4. So unlike here and there, where this limits at negative 3 and negative 1 respectively, they both coincide, meaning they both equal the same value on the left and the right. This one's they don't. Right? We can all agree negative 1 does not equal 4. So whenever we have this situation, I always say we have mean girls. The limit doesn't exist. So when they both don't equal each other, the answer is really just that. Limit does not exist. Okay? So that's a brief introduction of what we're going to be talking about in this section here. Okay. So let's now talk about this. So let's go over the actual, mathematical portion without the walkings and all that fun stuff. Okay? So definition of a limit. Suppose that a function f is defined for all x near a value of a. So in layman's terms, right, given a graph itself, this is what's going on. There's some values that are very, very close to negative 1 in both directions. I just fancy for saying that. Okay. So therefore, the definition of a limit is equal to this abbreviation like I talked about earlier. is, while x approaches a number on the x scale, on the x-axis, I want to figure out what is the y output, and that y output is actually L. So in our examples earlier, the L will be 2 and negative 3. And I could keep going here and there as well. So that's the actual definition of what a limit represents to a function. Okay. So the easiest way to find limits is by graphing. Graphing is always the best option to do so. Okay. So again, another way to describe a limit is as x gets closer to the value of a, which is arbitrary, some value of a, the function f of x gets closer to the value of L, meaning the output is equal to L. Okay. So how does this apply? So what we'll do is do a couple examples illustrating this. Let's suppose we have this function here. So given the graph, we want to find each individual one. So we want to find the limit as x goes to 3, so 3 is right here, of our function. So what's our output? So again, going back to our definition, that means if I walk in this direction, and if I walk in that direction, they go to the exact same number. So if I walk in both directions and I stop at exactly 3, my output both would be 0. So this answer would be 0. And the same thing applies for the next one, for negative 2. So if I walk this direction towards negative 2, and then that direction towards negative 2, they both coincide to be a y value of 0 as well. Now if x approaches 0, remember 0 is exactly in the middle here, so this is 0. So if I approach 0 on this side and 0 on that side, walk, 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 right, in both directions, I stop exactly at 0, and then what's my output? So my output is 1, 2, so it'll be 2, because that's what I see. Just like we talked about in the previous one. Okay. Now, this is actually not that bad. When you're given a graph, you can kind of tell and visualize what's going on. You write this motion and the arrows pointing in each individual direction. But the problem comes into play is, well, what if you're not given that? What if you're given the actual function themselves? So kind of like this, and ask the same question. Well, what value does it approach itself? Okay. So to do so, we're going to do the basic core of a limit, right? According to its definition is, like up here, as I get closer and closer and closer, let's say 0. Well, if I get closer and closer to 0, I'm fitting individual values closer and closer in both directions, right? And that cross process comes into play here. This is called the box method. Okay. So the box method basically says is, I'm going to put the value I want right in the middle, which is 1. And I'm going to pick numbers to the left of it and to the right of it and plug it into the function and see what they arbitrarily get closer to, because graphing this will be an actual pain, so we do the old-fashioned way, plug and chug, basically just another T-chart. Okay. So let's see what we get. So if we plug in 0.9 into our function right here, you get about 2.71. And if I plug in 0.99, we get 2.97. Let's get even closer with 3 nines. And in fact, you actually get pretty much the same thing. Again, always plugging it back into our original function here. So these are all on the left side, which kind of makes sense, right? This is the left side. And now we're going to do the right side. So for the right side, I just something a little bit bigger but very, very close to it. Okay. And the same thing, we're just going to plug it back into our original function and see what happens here. So I'll go this way. So I'll start 1.1. We get about 3.31. I'll get even closer. So this gives you 3.03. And then one more time for practice sake. And this gives you basically 3. So, just like over here, I want to see what f of x value I approach as I get closer and closer to this one. And it looks like if I just round, it looks like it's going to be 3 on the left-hand side. And again, going this direction, just following the same direction we did earlier on the right-hand side, it looks like it's also going to be 3. So therefore, this limit is going to be 3. Even though we have a hole in the graph because it's undefined at that point, we have an actual portion, literally just a hole, like we would have here and here. Okay. So that's what the difference between a limit and just plugging in a value in is. What is it approaching instead of just what's the actual value itself. Okay. So let's try some more out. Okay. So let's find the limit as x approaches 0 of this function. Okay. Now it's not, you don't have to do always 6 values. Usually 4 values is enough. So again, 0 is in the center. We'll pick some left numbers and some right numbers for x, and we're going to plug it into our f of x, meaning plug it into here. Alright, so now this is, you got to be careful, right? This is a number line, just like it's the x-axis. Here's 0. Numbers very close on the right hand side will be 0.01 and 0.1. Numbers to the left of here, it's actually negative 0.01 and negative 0.1. Again, right, it's a straight number line. Okay, so now we just plug it in. So I'll go from the left-hand side first. So we get about 1.87. And if I go even closer now to negative 0.01, I get 1.98. Okay, so it looks like that's getting closer and closer to, it looks like 2 on the left-hand side. Let's see if it goes and follows on the other side as well. So let's see. So I'll put 0.1 first. Let's see what this gives us. So we get 2.14. And next one is 2.01. So it looks like on this side, so the left side, just like it was a graph, I approach it. And on the right side, as I approach it, looks like it's also going to be 2. So therefore, this limit is equal to 2. Okay. So let's try some more. All right, let's make a box. Again, this is 1, so we could use the same templates we have up here. So this is 1. So we'll use these 4 here. Okay, and now we'll just go. So we'll go from the left first, and we'll do the right. So 0.99. This gives us approximately 0.501. Get even closer with another 9. And it's pretty much exactly 0.5. That's interesting. Okay, so I'm not really sure what's going on. Maybe it's, it could be decimal, so maybe it's 0.5. Let's go the other way just to make sure we're doing everything correctly. So on this side, I get 0.498. And if I go a little bit closer, I get 0.4999. So it looks like this way I get 0.5 because it's pretty much exactly. And on this side I also get 0.5. So it looks like this limit is 0.5 or half. Okay. All right, let's try this one now. Okay, 0's in the center. And we'll use this template here, right? So numbers really close to 0 on the right-hand side. I'll get even closer. Okay. All right, so let's see what we get. So let's plug in, and again, I'll just keep going with the same pattern. Plug in the left first. And I get a really big number. We'll get negative, I think 100. And plug this in and just 1 over it, so it gives you negative 1,000. That's interesting. Let's go on the other side. It is just the opposite. I get positive this way and 1,000 that way. That's interesting. Now what's going on? Now notice it's getting larger and larger in this direction. So if I get even closer, let's say I put instead negative 0.00001, even smaller, I get like negative 100,000. So what's actually happening is back over here, it looks like we have a vertical asymptote. It's going bigger in the negative direction. Well, we talked about that earlier. If it goes negative in the negative direction, that symbol represents negative infinity. So in our case, it looks like this is going towards negative infinity. On the flip side, these are getting bigger positive. And the same process. If I plug in 0.000001, I get positive 100,000 million portion. So now it's going larger in the positive direction. So in this direction, I go towards positive infinity. Well, we talked about this, right? If they don't go to the same thing, one's positive, one's negative, meaning they kind of look like this. Actually, this is what we get. So on the one side it's going towards negative infinity, on the other side it's going towards positive infinity. So because they don't go to each other, we say the limit does not exist. Or in other words, Mean Girls. So, what does that actually talk about? Okay. Now, interesting enough, right? If I on the left side it agrees, on the right side we have something else, but in between it isn't. But what are these called? Okay. So if we go back to our earlier example, we talked about left and rights. Okay. So actually, those left and rights are really called one-sided limits. So on one side it goes this way, on the other side it goes another way. But together they might not equal, but we could do each one individually. And that's pretty much now what we're talking about here, the one-sided limit part. Okay. So again, one-sided limit means as I go from the right-hand side or the left-hand side. or something called the right and left-sided limits. Now, if I want to go from the right-hand limit, meaning again, if I go back over here, all the right ones, meaning you're coming from the right-hand side, that represents the number with a positive above it. And if you're going on the left side, that represents a negative, as in like a little exponent, to signify left and right. So on this case, for example, if we go back over here, if I want to look at, let's say, again at -6 portion, well, if I now want to change this up and say I want to approach -6 on the left-hand side, I would pop a little negative right there, like a little exponent. Now it's saying, okay, on the left-hand side, what is this answer? That would be -1, because it's on the left side. But if I want to go from the right-hand side, I change that to a plus. Now I go this way, and I walk, and I see 4. The answer would be 4 in this case. So individually, we have answers that, as you could see all the way around, right? But together, because they don't coincide, that would not be correct. So, for example, or actually, let's do this. Scratch this off. Let's do that, yeah. So this doesn't work right here. Okay, here we go. So as I approach it from the left side, going in this direction, to 3, what do I see? So if I go across, that gives me 1. It means, and if I approach it from the right-hand side, going in that direction, I stop here, right at 3, and that corresponds to 1, 2, 3. So just like our previous example, left and right conclude but. So if I had a C part here, though, where it said, what's the actual limit as x goes to 3 in any direction, right? It has to be, so both have to coincide. Since these do not equal each other, therefore, again, the limit would not exist, meaning there's no limit. Okay? So that corresponds to our next little theorem, saying if the true limit exists if the left-hand side and the right side go to the exact same number. If they don't go to the exact same number, then this one does not exist, or Mean Girls. Right, so let's go back to our situation. We talked about going to infinity, right? So now we're going to talk about those kind of things. When is it? How do you know if it's going towards infinity or going towards a number, like here, there, and there, right? And those are called infinite limits. Okay? So let's look at this situation here, 1 over x squared. Okay? Well, let's make a box. That's the only thing we know, because we're going to find the limit. We have 0 here. All right, and then we're going to plug the x, f of x, and just like last time, we'll just use the same ones as previously. Okay. All right. So let's plug in each one individually. So the first one, that's going to give you a positive 100. This is going to be 1,000. And notice it's getting bigger. And it really doesn't matter, because if it's squared, it's going to be positive. And this actually matches. So you may think, oh, it's going to be 1,000. But just like last time, if I plug in negative 0.00001, and same thing on this side, positive 0.0001, you're going to get the same result in matching format. Okay? Now the reason for that, unlike the last situation, the graph goes like this. Meaning now, this time, this one's going towards positive infinity, and then the other side is also going towards positive infinity. So because they both match, and they both have the same sign, this is going towards positive infinity. Why? Because, again, we have a vertical asymptote at 0. So that's kind of situations that correspond here. So now limits can go to a number, they cannot exist, and they can also go towards the symbol of infinity, meaning they just go on for forever, or negative infinity. Okay, so let's look at this question 3. So given the graph of the function, which is a horrible graph to begin with, we want to find the limit as goes to -1 and 3. So here's our graph. So we want to go from x goes to -3, or positive 3 and -1. So let's look at the individual one. Here's -1. So as I approach it from the left-hand side, it just goes down. So it looks like on the left it's going towards negative infinity. As I approach it from the right-hand side, this way, this is also going towards negative infinity, which means my answer would be negative infinity in both directions. Now let's look at positive 3. So here's 3. As I approach it from the left-hand side, it shoots up, so it looks like it's going to positive infinity this time. And on the right side, again, it also shoots up to positive infinity. Since they're both positive, which that means my answer is going to be positive infinity. That's the outputs I would see of this graph. So let's go back to this one-sided stuff. Now, one-sided limits will always have an answer. So when it comes to one-sided limits, we can have an actual number, or we can have plus or minus infinity, depending on the situation we have. Okay? So if we look at example 2 here, and we want to find the limit on the plus and minus portion. Now, usually, because we only want right side or left side, I only have to do one side of our box. I only want I want the positive part, so that means the right-hand side. Plus means right-hand side. So numbers on the right of 0, so 0.001, 0.01. And then we just plug it in, so positive 0.01. Let's see what we get out. So this is going towards, I think it was really big 100 value. Oh, it's actually, sorry, 501. Plug in this, you get 5,001. And if again, notice, I get closer, I get bigger, bigger, bigger. So as I approach this value, it looks like this is going towards positive infinity. And on the other hand, you do the same thing for the other side. This I would want a left side limits because it's negative, so 0 goes on this side. I want only the numbers on the left-hand side. So negative 0.01, negative 0.001. And ironically enough, it's the same thing, but just the opposite, just going to be negative instead. So it'll be negative 501, negative 5,001. So it looks like this is going towards, again, infinity, but it's going to be the negative of it instead. So negative infinity will be the answer. And same process goes here as well. Okay, I want the left side of 2, so only the left side of 2. So numbers to the left of 2 will be 1.99, 1.999. And again, all we're going to do is just plug them in respectively. Okay. So these get even larger in portion, or actually negative larger in portion. So if we plug in 1.99, you get a really big number. What is it? Oh, okay. 2,000 something, 5 or something like that. And this gets even bigger, like 20,000. So this going towards, well, actually, sorry, negative. This becomes negative here. So this goes towards negative infinity. And again, on the flip side, it's actually the same process, but it now becomes positive instead. So we want right side, so numbers bigger than it, but very, very close to it. So there's a sign just flips. So as they go this way, this go towards positive infinity. Okay. All right, last situation here. So same situation. We have -4, but on the left, so only numbers on the left of -4. So for example, -3.99, -3. Oh, to the left, my mistake. Let me redo this. So -4. So it's going to be -4.01, -4.001, and this one's going to be the opposite. Okay. So again, all you have to do is plug these in, and you actually get a positive number out. So this function actually goes towards positive infinity, and believe it or not, in both directions. So in this case, it goes to positive infinity, and the other case it goes towards negative infinity. Now, that's all fun and dandy, right? But wouldn't it be nice if we don't have to do this box method over and over again to solve? Because, that's actually a lot of work, especially, plugging in the calculators. All this work can be pretty menacing and tedious, right, when it comes to it. So, the best part is about limits is, well, same process. Math people are very lazy, so they find shortcuts. Okay? So this is our shortcuts when it comes to limits. But again, this only works, however, if we have a polynomial. That's the key thing. A linear function or a linear or polynomial. So in other words, things like this or anything of this works. Right, where this could be any power. So kind of like that. Okay. Now, basically what all of this limit laws is basically saying is all I have to do is plug in the actual x value in for f, and that's it. That's exactly going to be our answer. But the problem with that is again, it only works if we have situations like this. Okay. Now you'd be wondering, well, why couldn't we do it the other times? Why we had to do the box method the entire time and not just do this? That's a great question. So like I said, it only works for polynomials, but let me make it more precise. The only time it will not work is if we have this situation. So we have something on top and the bottom looks like this, where I take the limit as x goes to a, meaning the same number is being added or subtracted there. What that means is I get 0 on the bottom, which is a big no-no. So the only time I can just plug in the number is if I have this situation happening. And if I have this situation happening, I got no choice but to do the box method and break it up to see what it actually works out. So for example, here would be a situation we cannot do. Because if I plug in -4, I actually get 0 on the bottom, which means we actually had no choice but to do the box method for that situation. Okay. Same applies here. If I plug in 0 in for x, I get 5 on the top, but I get 0 on the bottom, which is a big no-no, so it doesn't work. And actually notice for these as well. Okay. So, how would it look like when I can plug it in? Well, things like this. So for instance, if I just plug in 5 in for x, just like if it was f of 5, I get 5 over 3 plus 3. So as long as I don't get 0 on the bottom, we're done. So that's exactly it. So putting these together, that gives you 9, so it gives you 14 over 3. That's our limit. Isn't that much nicer? Okay. So plug in -1, it's a linear, so we could just straight plug in. This gives me 3, that still gives me -1, so it's 2. Alright, same thing, linear, so I could just plug it in. So 2 minus 2 to the third squared. So this is going to be 2 minus 8 squared. So -6 squared, so it's going to be 36. Plug in 1, perfectly fine. There's no fraction, so 3 times 1 is 3. And I don't know what cosine 1 is. You just plug that in the calculator to get your answer. Okay. Keep going. So now we have a fraction, but we just got to be worried. So we're just going to test it out. We're just going to plug in 0 to see what happens. So if I plug in 0, I get 0 minus 11 on top. And the bottom I get 0 minus 1. Good. As long as I don't 0 on the bottom, I'm good. So this becomes just 11. Check. It works. And then finally the last one. So again, we have another situation. Just got to verify. So plug in 3, that's 12 on top minus 4. And on the bottom, that gives me 9 times 5 is 45 minus 36. Good, right? Because that doesn't give me 0, which is all that matters. So on the top I get 8. And on the bottom I get 9. And there we go. So that's really nice, right? Plug and chug is the easiest way to do so. Okay, so last part when it comes to one-side limits is, well, it's nice when they give you the graph. It's not so nice when you actually plug in the one-sided, right, the box method. But what does plug and chug mean for the one-sided limits? So in other words, can we do this here for one-sided when it has a plus or minus there? And we actually can. Okay. And most of the time you're going to be given a piecewise function like this. So in this case, we want to find as x approaches -5 on the left-hand side. So all I go over here is, well, what are the left-hand side of -5? Again, it's a straight number line. Numbers on the left of -5 are -6, -7, and those values only hold for the first one, right? Those are less than -5. So I can now plug in -5 into here because this works on the left side. So it's just a constant, so it's just going to be 0. In fact, if I take the limit as x approaches any number like -7, it's still going to be 0 because on the left-hand side, it's still going to be 0 because it's always going to be 0, right? It's a constant. On the flip side, I want on the positive, so on the right-hand side. So numbers on the right-hand side of -5 are, let's say, -4, -3, -2, -4, -5, and let's say also 10. Way down here, 10 works. Well, we kind of have a contradiction now, because all of these numbers work for the middle one, and all of these numbers over there, like 10, work for that one. So the question is, which of do I choose, the middle or the bottom? Now again, this goes back to the definition of a limit. Limit says as you approach the value. So in other words, really close to -5. So the numbers that are really close to -5, like -4, only satisfy the middle part. So I only plug it in to the middle side. And again, I plug in -5 into now to the middle. And that means I also get 0. And now final answer is C. Well, what is the actual limit in both directions, right? With no plus or minus. So again, this is saying, well, let's go back over here. Does the left-hand side equal the right-hand side as I approach them? Well, let's find out. So we got 0. So this answer was 0. 0. So since they actually equal each other, the true limit they both approach is 0. So that's how we do one-sided limits. And there we go.